people, having done the very chapter of relations and functions, we are now all set to apply all our concepts into the applications. Well, for that, here are your JEE main pattern questions to test your conceptual knowledge about relations and functions. Let's start with the first question, which basically is, as you can see from the relations portion of this chapter. It is saying that R is a relation on N. I hope you remember the meaning of what do we mean by a relation on a set. By that we just mean that R is a subset of N cross N. By the very first line I have deduced this particular information about this question. Defined by, now they are given how the elements of N are related to the elements of N, because mind it, both the sets involved as the first and the second are the set of natural numbers only. So, first element from this collection of natural numbers is related to the other member of the collection of natural numbers, provided the first number plus twice second number gives you an 8 as the answer. It is only then when x will be related to y and the ordered pair x comma y is going to come and land inside the set R, provided x plus 2y is 8. Then they are asking, such a relation's domain comes out to be what among these four? So let's start and see what is my set R, because I know that by domain of R, I mean that if R is a subset of N cross N, which implies R is a relation on N, then by domain of R, I am interested in collecting all those x coming from N such that x comma y belongs to R. That means if all the ordered pairs, if I observe sitting inside the set R, just pick up the first components of all those ordered pairs, collect all the distinct ones among them and make a set out of it known as the domain of R. Obviously, as you can see, in order to collect the first components of the ordered pairs sitting inside R, we should first be aware about what are the ordered pairs sitting inside R. Obviously, my R is a subset of N cross N. And so, if I am interested in the relation R, that is basically going to relate the natural numbers to natural numbers. So let's start with the very first natural number sitting in the first set, which is the collection of all naturals. The very first natural number is x equals 1. Corresponding to x equals 1, is there any y in the second set with which this x is related under this relation, which is saying that x is only related to y provided x plus 2y is 8. That means corresponding to x equals 1, I want a natural number which satisfies x plus 2y equals 8, which for this x becomes 1 plus 2y equals 8, which makes it y equals 7 by 2. And therefore, 1 is related to 7 by 2 under this relation. But this does not mean that 1 comma 7 by 2 is going to come and sit inside the relation R. Because inside R, we have only those ordered pairs sitting in N cross N such that x plus 2y is equal to 8. The first thing is that I just don't want that the ordered pairs x and y, the two components, should satisfy the rule. But I also want that the first component and the second component both should come from the set of naturals. Here 1 is related to 7 by 2, but 7 by 2 does not belong to n, which implies 1 comma 7 by 2 does not belong to the relation R. Therefore, corresponding to 1, x equals 1, the only y which satisfies the rule is 7 by 2. But 7 by 2 is not a natural number. That means 1 is not related to any of these under the relation R. Let's look if 2 is related to any of the natural numbers in the second set. So for x equals 2, I need a y which satisfies x plus 2y equals 8, by which I mean 2 plus 2y equals 8, which basically means 2y equals 6 or y equals 3. And 3 is very much a natural number, so for x equals 2, the y which satisfies x plus 2y equals 8 is y equals 3, which is sitting in the set of naturals in the second set, which implies 2 comma 3 is an ordered pair sitting in the set R, because corresponding to 2, I have found 3 to which 2 is related. So I have found one ordered pair successfully sitting in the set R. That is what is our aim, to find all the ordered pairs sitting in the set R, so that we can collect the first components of all the ordered pairs and form the domain of R. Corresponding to x equals 3, let's see if there is any y working or not. For x equals 3, I want 3 plus 2y equals 8, which implies what is 8 minus 3 is 5. So you get y equals 5 by 2. That means 3 is basically giving rise to y equals 5 by 2, which satisfies x plus 2y equals 8. That means 3 is not related to any of the natural numbers in the second set. It is actually satisfying the relation with 5 by 2 acting as y. But 5 by 2 is not a natural number. And therefore, yes, the ordered pair 3 comma 5 by 2 does satisfy this rule, but is not coming from n cross n, and that is why 3 comma 5 by 2 cannot be kept inside the relation R, because inside R we can only borrow members from n cross n and keep it. That's why from 3 there is no arrow emerging to end in the second set n, because 3 is related to none of the members in the second set. For x equals 4, if I try and check, I have 4 plus 2y equals 8. 8 minus 4 makes it 4, and then y comes out to be what? 8 minus 4 is 4, 4 divided by 2 comes out to be 2. And this implies your 4 comma 2 is very much inside R. Because corresponding to 4, the natural number with which 4 is related, satisfying this relation is 2. And that is why 4 comes out to be related to 2. Because when x is 4, y is 2, your relation gets satisfied such that x and y both are coming from the set of naturals. If I start with x equals 5, you have 5 plus 2y equals 8. 8 minus 5 makes it 3, and y turns out to be 3 by 2. Again not belonging to n, which implies 5 comma 3 by 2 does not belong to R, and that also means 5 is not related to any of the terms in this set. Going to the last, or let's see if it is last or not, the member 6. For x equals 6, I want a y such that 6 plus 2y equals 8. Now 8 minus 6 is 2, so y comes out to be 1, which is very much inside the set of naturals, and this means 6 comma 1 is sitting inside the relation R. If I try for x equals 7, I have 7 plus 2y equals 8, making y equals 1 by 2, which is again not sitting in the collection of all naturals, which implies, yes, 7 comma half is very much satisfying the rule of x plus 2y equals 8, but this ordered pair does not come from n cross n and therefore cannot sit inside R. Moving to x equals 8, I want a y such that 8 plus 2y equals 8. And this means you get y equals 0. Now 0 again is not a natural number. And that is why 8 is not related to any of the natural numbers in the second set. If you go on proceeding like this, for x equals 9, for example, you are going to get 9 plus 2y equals 8, giving you y to be negative half, which is definitely not a natural number, and this process is going to continue because now this term is going to be greater than 8. So when you will subtract this term from 8, you are going to get negative terms, and that is why this can never ever be a natural number. Therefore, our process got terminated at 6. For x equals 6, we got 1 such that 6 comma 1 is in R. For 7, for 8, for 9 and so on, there are no natural numbers to which they are related. And we got answers for 4, for 2, and that's it. So we got that 2 is related to 3, yes. We got 4 is related to 2, yes. And we got 6 is related to 1, that's it. So the arrow diagram in this case, if I try and draw with the help of the arrows, I get this 6 in the end is just related to 1, and these are the only 3 ordered pairs sitting inside the set R, which are 2 comma 3, 4 comma 2 and 6 comma 1. Now that you have your R with you, what do you think is the domain of R, when I have already told you that inside the domain we just collect the first components of the entire relation. So the first components happen to be here as 2, 4 and 6, and that is what is my domain of R. The set consisting of 3 members, 2, 4 and 6. Let's see if this set is given as one of the solutions or options or not. The first option talks about saying that domain is consisting of 2, 4 and 8, which is absolutely wrong. Second talks about 2, 4, 6 and 8. So yes, it is saying 2 is there, 4 is there, 6 is there. I don't want 8 over here. This is also wrong. The third one, yes, is what is my solution, and therefore that is the correct option, with D also happening to be wrong. That is how you deal with the questions involving to find out the domain of a relation. Why don't you take a sec or two to copy it, and then I am going to proceed with the second question. If I try and begin with what is the second question, you have to first of all understand that it is very important to brace your concepts up about relations and functions. Because until and unless your definitions, your concepts, the ideas are not clear, you won't enjoy the question solving sessions. Beginning with the solution of the second question, which is going to come our way, let's see what it is turning out to be. It is saying find the domain for which fx equals 2x square minus 1 and gx equals 1 minus 3x are equal. You have to find those values of x for which these two functions are equal. So let's start with the solution. I need to find x for which fx is equal to gx, for which x. That is my question. So let's just substitute and see what are those x's which are making f and g equal. Fx given to you is 2x square minus 1. Gx given to you is 1 minus 3x. These two are equal for certain x implies they are giving rise to this expression to be true, which is 2x square plus 3x minus 1 equals 0. So if for certain x fx is equal to gx, this implies for that x 2x square plus 3x minus 2 should be 0 definitely. Now this is nothing but a quadratic equation. We know how to break the middle term. So let's do that and get the solution for x if it exists in R. So let's break the middle term. This will be 2x square plus 4x minus x. 4x minus x is going to deliver you 3x, and 4 into minus 1 will be minus 4, which you want. So you will have this. And then just take out the common term. 2x comes out to be common. You get x plus 2 inside the bracket minus 1 x plus 2, which becomes, just collect the common terms. You get x plus 2 and 2x minus 1 left. Now this can be 0 provided x is minus 2. That means this term is 0, which means x is minus 2, or this term is 0, which means x is equal to half, because 2x minus 1 equals 0 gives x equals half. This means for minus 2 and for x equals half, I am getting LHS to be equal to 0. That means I am getting this LHS equal to 0. That means for these two x's, I am getting this LHS equal to 0. And for the same x's, I am getting all these LHS equal to RHS, which is 0, which means for these two x, I am getting fx equal to gx. And thus, it is these two x which can make or have the power to make fx equals gx. For these 2 points only can my f be equal to g, and therefore the domain happens to be just consisting of these 2 points for which f and g can be equal, which is minus 2 and half. Because domain of f and g should be same if you wish to talk about f being equal to g. And therefore, the domain for which the functions fx is equal to gx is the set minus 2 and half, and that makes option B to be the correct option. That is how you have to proceed while solving questions concerning to find those values of x's for which 2 functions come out to be equal. Take some time, spend some time to understand the concept that I have used over here and write them down in your notebooks, and then we will be proceeding with the third question. Let us begin dealing with the very third question. And what does that has to bring for us is what we have to find out. The third question again is dealing with the concept of domain. It is saying what is the domain of the function which involves a log term in the numerator and a quadratic equation in the denominator. So for fx to have a domain, by domain of a function we mean those points, those inputs for which the function is delivering real outputs. That means if for a certain x, fx comes out to be undefined or non-real term, that x will not get an entry inside the input set of f, which we call the domain of f. So basically we have to find for which x is this expression turning out to be valid. Now if you remember, while confronting many of the rational expressions in the chapter functions, I told you where does the problem come in rational expressions. Over here I have log to the base 2 x plus 3 whole upon x square plus 3x plus 2. For this expression to be defined, I have to find out for which x is this expression coming out to be sitting inside R. So this expression sits inside R for which x is what my query is, because only those x's which deliver this particular expression inside real numbers are the x's which are going to get the entry in the input set of f known as the domain of f. Now you know this rational expression is defined only when the denominator is non-zero. So for fx to belong to R, firstly x square plus 3x plus 2 should be not equal to 0, which implies x square plus 2x plus x plus 2 should be not equal to 0. This means x plus 2 plus 1 into x plus 2, this should not be equal to 0. I am just breaking the middle term, solving this quadratic equation, which implies collect the like terms, you get x plus 2, x plus 1, this should be not equal to 0. And this expression is 0 only when x is equal to minus 2 or x is equal to minus 1, and this implies x is not allowed to be minus 2 and x is not allowed to be minus 1, because if x is allowed to be minus 2 or minus 1, this expression will be 0. And I don't want it to be 0, because this 0 implies this 0 implies this 0 implies this 0. And if the denominator turns out to be 0, my function will not be sitting inside R. That is why for fx to belong to R, firstly I want that my x should not be equal to minus 1 and minus 2. Done? Problem solved? Not yet. Because if you look above carefully, I am given log function with base 2, and if you remember, for log x to the base a greater than 1, the graph of log was like this. At 1, log was 0, and in fact, the domain of log x to the base a is always equal to this. Only on positive reals is log applied or applicable. That means when you are talking about log x, over here as x, only those members can enter which are coming from the interval 0, infinity. If there is any real number not belonging to 0, infinity, it cannot go and sit inside log x. That means log of x plus 3 to the base 2 is defined only when x plus 3 belongs to 0, infinity interval. That is what I will write now. I'll write but log to the base 2 applied to x plus 3 is going to give you real output only when x plus 3 comes from the domain of this log function, right? Which implies x plus 3 should belong to 0, infinity, because that is what is the domain of log. Which implies x plus 3 has to be strictly greater than 0. Which implies x has to be strictly greater than minus 3. So, both numerator and denominator are giving me conditions for x. Denominator should be not equal to 0, which means x should be not equal to 1 and x should be not equal to 2 for this expression to be a valid expression sitting inside the set of all reals. But also I need that x should be strictly greater than minus 3, because if that is not the case, this expression only won't be defined. And if the numerator is undefined, even if the denominator is defined, the entire expression becomes undefined. So both of them are creating individually problems for f to land inside R, and that is why we have to deal with both of them individually. We have got that x should not be equal to minus 1 and minus 2, and we want that x should be strictly greater than minus 3. So on the real line, if I try and see, this is minus 1, this is minus 2, this is minus 3. I want my x to be strictly greater than minus 3, but I want it to be not equal to minus 2 and not equal to minus 1. That means I want that for fx to belong to R, my x should come from minus 3 comma minus 2 open union minus 2 comma minus 1 open union minus 1 comma infinity. Or I can write it as from minus 3 to infinity. If I consider the entire interval and remove from it minus 2 and minus 1, I can write this alternatively as this, and this is the collection of all those x's for which the domain is not creating a problem, or the numerator is not creating a problem, and the denominator is also not creating a problem, which means it is these x's for which f of x is delivering real values, and that is why it is these x's which get an entry in the domain of f, and therefore this is what becomes my domain of the function f, which is minus 3 comma infinity minus the set of minus 1 and minus 2. Let's see if that is given in the options, which is very much given in the option number D, and that is what is my correct answer. Dealing with the next question, which is question number 4, it would be very important for you to spend at least a minute or two with this question, understand how the domain and the codomain of the function is very, very much important to be subsets of the real line. And only those x's which make fx fall inside the collection of all reals are the x's which qualify to get the entry inside the domain of f, and it is based on that particular concept that we have found our very domain of this function. The next question deals with again relations. It says that if A is this set, B is this set, C is this set, what do you think is A minus B cross B minus C? For this concept, you should know first of all what do we mean by Cartesian product of two sets, which is over here set number 1 being played by A minus B, set number 2 being played by B minus C. And once you know what is the Cartesian product of two sets, where you have also found out what is my first set under these concepts, what is my second set under all these definitions of A, B and C, we will have this entire set calculated with us. So if A is 1, 2 and 4, set of 3 naturals, B is given to be 2, 4 and 5 and C is given to be 2 and 5. In this case, I am interested in calculating A minus B cross B minus C. Let's see what is A minus B. That means from A, which is 1, 2 and 4, remove the contribution of B. That means if there are any members of B sitting inside set A, remove them. Inside set B sit 2 and 4 which are sitting in set A. So remove 2 and 4 from A to get A minus B, which is singleton 1. The second set, which happens to be B minus C, is calculated when from B, which is 2, 4 and 5, you remove the contribution of C, which is 2 and 5. That means members which are sitting in C, if they are sitting in B, remove them. Only 2 and 5, that is both the members of C are sitting in B, remove them, you get this. And then you know what do I mean by arbitrarily A cross B. It is the set of all those ordered pairs x comma y where x is coming from A and the second component comes from the second set. And therefore A minus B cross B minus C is the set of all those ordered pairs such that the first component comes from the first set and second component comes from the second set. But what is A minus B? A minus B is singleton 1 cross singleton 4, which is my B minus C. And therefore this happens to be the collection of all those ordered pairs x comma y such that x is coming from singleton 1 and y is coming from singleton 4. That means x has only one possibility, which is 1, and y has only one possibility, which is 4. Therefore, the only ordered pair x comma y such that x belongs to singleton 1, y belongs to singleton 4 is the ordered pair 1 comma 4. And therefore, this set is going to contain just this one ordered pair, and this is my set A minus B cross B minus C. Let's see if this is sitting as one of the options given or not. I want singleton set 1 comma 4. Singleton set inside which is the only ordered pair 1 comma 4 sitting is my correct answer. If you look at option number C carefully, it is saying the answer is 1 comma 4. No, this is not the correct answer because I want a set in which are sitting ordered pairs, and this is not a set and I need a set, and therefore C is definitely wrong. That is what is the difference between an element and a set consisting of an element. That is why A is correct, C is wrong, B is wrong and D is definitely wrong. That is what brings me to the end of solution number 4. Now that we have dealt with question 4, understood how do we actually compute this type of relations, it's time to get on along with question number 5. Dealing with question 4, we have understood that Cartesian product of two sets, this concept and the concept of removing a set's contribution from another set is what was important for getting the solution of this question. Let's get along with question number 5 and let's see what that has to bring for us. Question number 5, if I try and understand, is I am given a function with variable as theta. Just look over here. It is theta. When which you input inside f, you get f of theta like this. It is saying if f of theta is this particular expression, sine theta into sine theta plus sine 3 theta, then f of theta behaves in which manner? How does it behave? What is its range? Is what the function is trying to ask you. Let's copy f of theta and then start with the solution. The function given to me is that when you input theta, f of theta, which is the output, turns out to be sine theta multiplied by the expression sine theta plus sine 3 theta. Now obviously it's trigonometric terms getting involved over here. For that, let me give you a small concept. This concept speaks about the formula of sine 3 theta, which will be used over here to solve this. Sine 3 theta is 3 sine theta minus 4 sine cube theta. If I use this identity over here, I get my f of theta is sine theta. Inside the bracket, I already have 1 sine theta, copy it, plus use the identity over here. You get 3 sine theta minus 4 sine cube theta. And now you have sine theta plus 3 sine theta give you 4 sine theta minus 4 sine cube theta. Just let this sine theta get multiplied inside the brackets. You get 4 sine square theta minus 4 sine to the power 4 theta. This has increased the power by 1, increases the power by 1. This becomes 2, this becomes 4. You get 4 sine square theta common. After that, you're left with 1 minus sine square theta. And this expression, if I am not wrong, reminds me of another identity. We all know that sine square theta plus cos square theta is 1, which implies 1 minus sine square theta is nothing but cos square theta. So using this particular identity, after using this identity, I am at this note of 1 minus sine square theta, which is nothing but cos square theta, giving me the expression 2 sine square theta cos square or 4 sine square theta cos square theta. And this is what? This is nothing but 2 sine theta cos theta whole square. That is what it is. Because if you open it up, you get the same expression. And 2 sine theta cos theta, again if I use the identity, it is sine 2 theta, which is 2 sine theta cos theta. And so this expression becomes sine 2 theta whole square. Whatever theta you put over here, the square of any expression is always non-negative. So this is going to be non-negative always for any theta you pick up from the collection of all reals. And that means whichever theta you are going to put as input inside f, f of theta is always going to turn out to be non-negative. Let's see if that is given as an option in this question. The first one says that f of theta is non-negative only when theta is non-negative. That's not true. F of theta is less than equal to 0. That is absolutely wrong. I am getting greater than equal to 0. Third one says yes, it is greater than equal to 0 for every real theta. That is what is correct, and D is again wrong because it is dealing with f theta being less than equal to 0. That is how I deal with the question number 5 by using 3 identities that I told you from trigonometry. Just the usage of these 3 identities is going to make the solution of this question a cakewalk for you, and you will sail through it and attain the answer as the very correct one. And therefore, it is very important to understand the identities used in trigonometric expressions so that directly just by looking at the expressions, we are able to know which identity is supposed to be used where and then get along with our question. Question number 6 now again deals with relations. It says if A and B are 2 sets containing 4 and 2 elements respectively, then the number of subsets of A cross B. Can you identify something with the number of subsets? Well, number of subsets of A cross B, each having at least 3 elements. I am basically trying to understand something about subsets of A cross B when given A has 4 elements and B has 2 elements. This question is trying to give us the information that cardinality of A is 4 and cardinality of B is 2. A has 4 members, B has 2, and this implies A cross B has how many members? Well, that is what is the cardinality of A cross B, which is cardinality of A into cardinality of B, which is 4 into 2, which is 8. So, if A has 4, B has 2 members, A cross B has 8 members, and thus number of subsets of A cross B having 8 elements is what? Well, I know the rule that number of subsets of set A such that cardinality of A is given to be n. That means if A has n members inside it, the number of subsets of A is equal to 2 to the power n. And therefore, if A cross B has 8 elements, then number of subsets of A cross B will be 2 to the power 8. And 2 to the power 8 is nothing but 2 getting multiplied 8 times, which is 256. And that is why number of subsets of A cross B are 256 in number. There are 256 subsets of A cross B, where A cross B overall has 8 members in it. I want not all the subsets, only those subsets which have at least 3 elements. That means I don't want subsets which have 0 elements. I don't want subsets which have 1 element. I don't want subsets which have 2 elements. From 3 onwards, I want all the subsets. That means from the collection of all the subsets, I want to remove those subsets having 0 elements, 1 element and 2 elements. That means how many are the subsets having 0 elements, how many are the subsets having 1 element, how many are the subsets having 2 elements. Let's try and find that out. Before I get on with that solution, let me remind you the very concept of combinations which I taught you while teaching functions. I told you that if you have n members with yourself and you want to find out all possible combinations of n members taken m at a time, that number becomes NCM. Let me write that out. Let n and r be positive integers such that r is greater than equal to 1, less than equal to n. Then the total number of combinations of n objects taken r at a time irrespective of ordering. I am not concerned with ordering of those members like permutation. So, irrespective of ordering is equal to NCR, which is nothing but n factorial upon r factorial into n minus r factorial. So, over here, if I want to find number of subsets of A cross B having 0 elements, this means I want to make all the combinations of 8 elements sitting inside A cross B taken 0 at a time, and that is nothing but 8C0, which is 8 factorial upon 0 factorial into 8 minus 0 factorial, which is again 8 factorial. This gives me 1, because 0 factorial is also 1. If I have to find number of subsets having 1 element out of 8 elements, I want to find out those many subsets who have 1 element. They are what? That means out of 8 elements, what are the possibilities in which I can choose 1 element from 8 elements? They are 8C1, which is 8 factorial upon 1 factorial into 8 minus 1 factorial, which is 7 factorial, and this is going to give you 8. That means there are 8 ways in which I can choose 1 element from 8 elements, and that is going to result in 8 singleton subsets of A cross B. I don't want that, because inside singleton sets there are only 1 element sitting, but we want at least 3 elements to sit inside the set. So we also don't want those sets which have only 2 members. Let's find that number out as well. Number of subsets having only 2 elements is what? Obviously, out of 8 elements, choose 2 elements. This can be done in how many ways? 8 factorial upon 2 factorial into 8 minus 2 factorial, which is 6 factorial, and this number comes out to be 28. That means there is only one subset of A cross B with 0 elements, and we know what is that. That is the empty set. We have 8 singleton sets sitting as the subset of A cross B. Obviously, each singleton set consists of those 8 members which are making A cross B. And there are 28 subsets of A cross B consisting of only 2 members. I don't want all 3 of them, because none of them are containing at least 3 members. So, out of 256 subsets, the number of subsets which contain at least 3 members, what are they? They are 2 number of subsets containing at least 3 members out of 8 members of A cross B is, out of all the subsets of A cross B, remove subsets which contain 0 elements, subsets which contain 1 element, and subsets which contain 2 elements. And you are going to get this number as 219. Out of 256 subsets of A cross B, 219 subsets are like those which contain at least 3 members out of the 8 members in A cross B, and that is why option number A happens to be my correct answer. Because the question was to find the number of subsets of A cross B which have at least 3 elements. And that is what we have successfully found, that out of 256, 219 are the only subsets of A cross B having at least 3 members. I hope you guys must have understood the concept of combinations that I have used to find out as to how many subsets of A cross B will exist consisting of 0 members, 1 member, or 2 members. And now we are once through with question number 6 on the venture to start question number 7. It says the domain of the function y of x is given by the equation this is what? Well, this function is given in the implicit form. Remember, we had done implicit functions in which the dependent variable was hidden in the expression and the expression was not given in the form of y equals f of x. Here it is not given in the form of y equals f of x, it is hidden in this expression, y being the dependent variable, x being the independent variable, and x is standing for the input, y is standing for the output. The question says, what are the valid inputs? That means what are the valid values of x's for which this expression is true? That is what we have to find. So, here I am given the expression 2 to the power x plus 2 to the power y equals 2. This means if I want to find out x, I will just put x here and I will have 2 minus 2 to the power y. Now, if you remember, they are nothing but exponential terms. You know that if I have fx equals a to the power x, where a is greater than 1, then domain is what? Domain of this function is nothing but the collection of all reals, and the range of this function is this. So, over here we have 2 to the power x with us instead of a, there is 2 and it is greater than 1. The graph which will be formed is like this. Well, this is nothing but minus infinity. As you keep on decreasing your x, the graph decreases, reaches to, basically it keeps on decreasing. And as you increase your x, it keeps on increasing. At the point 0, the value attained is 1 because 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4. This means at the point 0, 2 to the power x is 1. At the point 1, 2 to the power x is 2. At the point 2, it's 3. At the point 2, it's 4, and so on. That is what is the behavior of the function 2 to the power x graphically. That means I know that 2 to the power x for every x sitting in the collection of all reals is always going to be greater than 0. That is what is the range, or if you can see the graph also, the entire graph is on the above side of the x-axis, implying that 2 to the power x is always greater than 0. This means what? 2 to the power y if I individually concern, this also means 2 to the power y is always greater than 0. This is also the exponential expression if I consider y as the input. So, this implies minus 2 to the power y is less than 0. And then this implies 2 minus 2 to the power y is less than 2. But 2 minus 2 to the power y is nothing but 2 to the power x, and I get that 2 to the power x is, yes, greater than 0 but less than 2 in this case. So, which are those values of x for which 2 to the power x is greater than 0 but less than 2? Well, 2 to the power x is between 0 and 2 for which values of x's? Well, it is between 0 and 2 when the graph is basically from here till here. It is this portion of the graph which corresponds to fx lying between 0 and 2, or 2 to the power x lying between 0 and 2. And this part of graph is corresponding to this part of the domain, which is whenever x is over here or over here up till 1, my fx will be over here from 0 to 2. That means whenever x belongs to minus infinity to 1, this implies 2 to the power x belongs to 0, 2. Because 2 to the power 1 is 2. That's it. The moment I go beyond 1, my output will be beyond 2. So I cannot go beyond 1 in the domain. Whereas, as much as I want to go to the left on the real line, I can go, because this graph is decreasing. It is less than 1 for every real on the left hand side. Definitely so it is less than 2 also. And that is why I get that whenever x is sitting inside minus infinity, 1, 2 to the power x is belonging to 0, 2, which is this expression. And that is why 2 to the power x is equal to 2 minus 2 to the power y for only these values of x, and this is given in option number D, as you can see. X is greater than minus infinity, less than 1 is another way of writing the interval minus infinity, 1, and therefore this is my correct answer. Spend some time, understand what I have done over here, because we were given an implicit expression and not an explicit expression. Understand what I have done, and then we'll move on to the next question. Let's begin dealing with question number 8. Question number 8 says that A is the set of those even natural numbers which are less than 8. So what does A become? By just this statement, A becomes all those even natural numbers which are less than 8. That means 2 comes inside it, 4 comes inside it, 6 comes inside it, and that's it. Because these are the only even natural numbers which are less than 8. And B is the set of prime numbers less than 7. Therefore, B happens to be prime number is 2 which is less than 7, 3 and 5. It is strictly less than 7, so I am not putting 7 over here. Strictly less than 8, that's why I am not putting 8 over here. If I have formed what is my B, I have formed what is my A, the question is number of relations from A to B. Well, we all know that number of relations from a set A to another set B is equal to number of subsets of A cross B. And I just told you that if you know the number of members sitting in a set, you can find out the number of subsets that set possesses. And if A has 3 members and B has again 3 members, this implies A cross B has how many members? Well, A cross B has cardinality of A into cardinality of B, which is 9 members. And if A cross B has 9 members, then number of subsets of A cross B are what? They are nothing but 2 to the power 9. That means number of subsets of A cross B is 2 to the power 9, or I can say number of relations from A to B is 2 to the power 9, because 9 is the number of members sitting in the set A cross B, and that marks option number A to be the correct option. That is how easily we dealt with this question, just by understanding what is the concept of number of subsets from a set A to set B, understanding the number of relations or number of subsets of the set A cross B. Let's see what is our next question. It is saying the domain of the function given by this expression is what? Again, understand this is made up of 2 different types of functions. One is the square root function and one is the logarithmic function sitting in the denominator. So let's start with the concept. We all know that the function log x, if I just take for a greater than 1, the graph comes like this of log x. Log of 1 is 0. And we all know log x to the base a is y if and only if a to the power y is x. That is what is the definition of the logarithmic function. And we also know that the domain of log x to the base a is 0, infinity. That means inside the log function I can only put those reals which belong to 0, infinity interval. Log x is not defined for negative reals. So for log of 1 minus x to exist, first condition is 1 minus x has to belong to 0, infinity, which means 1 minus x has to be greater than 0 or x has to be less than 1. Not just this, because this is sitting in the denominator, 1 upon something will be a real number only when the denominator is non-zero. And log of anything is 0 only when that anything is 1, because log 1 is 0. And for this expression to be non-zero, I want 1 minus x to be not be equal to 1. Because if 1 minus x is 1, log 1 will be 0 and 1 upon 0 will be an undefined term. So the second condition I want is 1 minus x should not be equal to 1, or I can say that x should not be equal to 0. Because when x is equal to 0, you get 1 minus x equal to 1. And now I have 2 conditions with me, that when 1 minus x belongs to 0, infinity and 1 minus x is not equal to 1, in that case 1 upon log 1 minus x to the base 10 gives you real answers. But for the same x for which 1 upon log 1 minus x gives me real answers, the same x's are getting incorporated over here inside under root x plus 2. And I know that the square root function, if I mark it as gx, this has domain again 0, infinity, and it goes to also 0, infinity as the range. This is what is the domain of G and this is the range of G. And I know that the graph of this square root function follows to be something like this. And therefore, under root x plus 2 can only be defined if x plus 2 comes from the domain of the root function, which is 0, infinity. So I want x plus 2 to come from 0, infinity, which is I want x plus 2 to be greater than equal to 0. But what happens if x plus 2 is equal to 0? If x plus 2 is equal to 0, this implies x is minus 2, which implies the first part of the function 1 upon log to the base 10, 1 minus x happens to be 1 minus minus 2, which is 3. So this is what you will get if x turns out to be minus 2. Over here you will get under root 0 and over here you will get 1 upon log 3 to the base 10. Now what is log 3 to the base 10? If I use this rule that log x to the base a is y, if and only if a to the power y is x, then log 3 to the base 10 is equal to that question mark such that 10 to the power question mark is 3. And this question mark that I have put is allowed to come from all reals. Is there any real number corresponding to which if 10 is raised to that particular real number as power, you get the answer as 3? Of course not. If there are positive powers over here, you are going to get numbers strictly greater than 3. If you put 0, you get a 1. And if you put negative powers of 10, you get expressions even less than 1. And therefore, it is strictly less than 3 also. That is why there does not exist any question mark in R such that log 10 to the base 3 comes out to be a question mark. That means log 10 to the base 3 does not belong to R. There is no real number which is equal to 1 upon log 3 to the base 10, which means x cannot be equal to minus 2, and therefore x plus 2 cannot be equal to 0, and thus this implies x plus 2 has to be strictly greater than 0. Which implies x is greater than minus 2 for the entire expression of f to be defined. And thus, for this expression to be defined, I want x should be less than 1 and x should be not equal to 0. And for this expression to be defined, I want x should be greater than minus 2. And when all three conditions are satisfied, my entire function is going to yield only real values. That is, x should be less than 1, the first condition. If I on the number line try and plot, x has to be less than 1, not equal to 0 and greater than minus 2. That means the set that comes out to be is minus 2, 1. From minus 2 to 1 is the common portion. Minus 2 to 1, and from it you just remove this 0. It is x which belong to this particular set, corresponding to which the function given is going to deliver real values, and therefore this happens to be my domain of the given f, which is from minus 2 to 1 minus, just puncture out the point 0. And that is given as your option number C. Successfully obtaining the domain for this function, which just used the concepts of square root function and the logarithmic function, we have come to an end of this question. Moving to the last question in the league, let's see what that decides to bring for us. But before that, mind it that your concepts about question number 9 are very, very clear. Until and unless you are aware about the behavior of the logarithmic function and the square root function, this question cannot be solved. Question number 10 again deals with relation. It says, if R is a relation from this set to this set. So let's say that this set is my set A and this set sitting here is my set B. By this rule that x is related to y if and only if x is relatively prime to y, then what is the range of R inverse? Again, the concept of R inverse is being used. R inverse is the set of all those ordered pairs y comma x such that x comma y is sitting inside R. Collect all the ordered pairs of R, swap the values of x and y, get the ordered pairs of R inverse. So to get R inverse, we have to first get R, which is a relation from set A to set B, where set A has 2, 3, 4 and 5 and set B has 3, 6, 7 and 10. Let's see what R is trying to say. The members of the first set will be related to the members of the second set provided the members of the first set are relatively prime to the members of the second set. That means the only common factor which both these members possess is just 1. Now 2 is relatively prime to 3 because only 1 is the common factor. 2 is not relatively prime to 6 because 2 is one more common factor apart from 1 between 2 and 6 and therefore 2 is not related to 6. 2 is definitely relatively prime to 7 again because they only have one common factor which is 1, and 2 is not relatively prime to 10 because 2 and 10 have 2 as one more common factor apart from 1 and therefore 2 and 10 are not relatively prime to each other. Starting with 3, 3 is not relatively prime to 3 because HCF of 3 and 3 is not equal to 1, it is 3. It is 3 which is a common factor between 3 and 3. So 3 is not relatively prime to 3. 3 is not relatively prime to 6 because 3 is a common factor of 3 and 6 apart from 1. 3 is relatively prime to 7 and 3 is relatively prime to 10. There is no common factor between 3 and 7 and 3 and 10 apart from 1. Starting with 4, 4 is relatively prime to 3. 4 is not relatively prime to 6 because 2 is a common factor. 4 is relatively prime to 7 and 4 is not relatively prime to 10 because again 2 is a common factor. Starting with 5, 5 is relatively prime to 3. 5 is also relatively prime to 6 and 5 is relatively prime to 7. But 5 is not relatively prime to 10 because 5 is a common factor in 5 and 10, and by just interpreting these arrows, I get my set R, which is starting from 2 there are 2 arrows, so I get 2, 3 and 2, 7. Then the next are 2 arrows from 3 terminating at 7 and 10, giving me 3, 7 and 3, 10. Then I have 2 arrows again starting from 4 terminating at 3 and 7, giving me 4, 3 and 4, 7. And I have from 5, 3 arrows emerging, 5, 3, 5, 6, 5, 7, these 3 ordered pairs I will be writing corresponding to these 3 arrows. This is my R, and I know that range of R inverse is domain of R, and domain of R inverse is the range of R. That is what is the relation between R and R inverse. If I wish to find the range of R inverse, I have to find actually the domain of R, which is, I just have to collect the first components of all the ordered pairs sitting in the set R. The first components are 2, 3, 4 and 5. The distinct first components happen to be 2, 3, 4 and 5. Do not allow repetition because sets do not allow repetition. And domain of R is very much a set which is equal to the range of R inverse. That is what we wished to find. Let's see if this set is in the solution set, option set or not. 2, 3, 4 and 5 is yes, sitting as option number D. And so this is what is my correct answer. Thus, dealing with the 10 questions, we have understood or basically brushed almost all the concepts related to relations and functions. Spend time, ample amount of time with these questions and practice nicely, because this is going to help you retain your concepts about this chapter for a longer period of time. I hope this was helpful. Practice nicely, study well and take care.